On November 30th, 3-Way Atlas is on an approach trajectory toward Earth, with only about 20 days left before closest passage. The United Nations has quietly turned Atlas into a full-scale planetary defense drill, while amateur images reveal an enormous main tail, a reverse tail pushing against the solar wind and unnaturally straight jets that hint at an internal energy source and propulsion with a technological flavour. Key milestones, the Earth flyby and the later crossing of Jupiter's Hill sphere, are seen as strategic appointments, pulling Juno Juice and the global amateur community into the hunt. Razor-sharp images from Paul Craggs, showing an elongated, symmetric, seemingly purposeful structure, stand in stark contrast to NASA's blurred, delayed-release driving skepticism and demands for transparency to a new peak, set beside recent UFO footage near the Moon. And the Navy-confirmed Trindade case, one question remains: is 3-Eye Atlas an extreme natural comet or a camouflaged shell hiding advanced technology? In 20 days, will 3-Eye Atlas really sweep past Earth as expected? And what will it reveal? Let's begin the investigation. The United Nations has quietly triggered the largest planetary defense drill in its history. Officially, the exercise is about readiness, but rumours say the real reason has a name: 3-Eye Atlas. 3 Atlas is the third confirmed interstellar visitor ever tracked passing through the solar system. On paper, Atlas is described as a faint elongated comet, following a harmless hyperbolic path that misses Earth by a safe margin. Those dry lines in the circulars sound reassuring, yet the scale of the response around Atlas feels wildly out of proportion. The International Asteroid Warning Network and several planetary defense offices have woven 3 Atlas into a full-scale rehearsal. Radar schedules are reshuffled, telescope time is commandeered, and emergency communication channels are tested as if 3 Atlas were a slow-motion incoming weapon. Behind closed doors, analysts run simulations of fragment impacts, grid failures, and supply chain stress tests, all key to the flyby timeline of Atlas. On the public websites, however, the alerts look strangely muted, almost casual in the way they mention 3-Eye Atlas. Press releases refer to a valuable scientific opportunity and a textbook case of international coordination, as if Atlas were just a convenient training prop. For anyone comparing the soft language to the hard mobilization, a subtle dissonance starts to ring around the name 3 Atlas. The object is officially non-threatening, yet the same dashboards used for genuine impact risks now track every tiny update in the orbit of Atlas. Some officials argue that you never waste a good rehearsal, that the passage of 3-Eye Atlas is simply the first real target big enough to unify the system. Others quietly note how carefully the briefings avoid a different word, the word interstellar, whenever they talk about Atlas to the general public. In technical memos, the origin of 3-Eye Atlas is front and centre, a guest from beyond the Oort cloud, an outsider that does not belong to our sky charts. In press conferences, the same origin is brushed aside, replaced with phrases like unusual comet, while questions about the true nature of Atlas are deflected. That mismatch becomes the first anomaly in the story, a social anomaly wrapped around a physical one long before any strange images of 3 Atlas reach the news feeds. Viewers at home are told to relax and enjoy the spectacle, while every major observatory on Earth quietly recalibrates sensors to squeeze more data out of Atlas. Somewhere between those two narratives, 3 Atlas stops being just an object and becomes a mirror reflecting how much our institutions are willing to say out loud. The next wave of observations will not calm that tension, because the first high-contrast images of Atlas are about to show something far less ordinary than a training target. The first truly shocking images of 3 Atlas did not come from a billion-dollar flagship mission. They came from backyard observatories, from people who dragged half-meter telescopes into the cold and pointed them at Atlas. On one November night, a Japanese astrophotographer stacked hundreds of frames and pulled a razor-sharp profile of 3 Atlas out of the noise. The processed image showed a bright condensed head, then a pale streamer stretching away from Atlas like a torn silk ribbon. When the scale bar was overlaid, the numbers forced everyone to pause. The main dust tail of 3 Atlas ran close to 5 million kilometers from the nucleus, a structure longer than the distance from Earth to the Moon, more than 10 times over. For a typical long-period comet, such a tail would already be impressive. For an interstellar visitor like 3 Atlas racing through the inner system on a one-time hyperbolic flyby, the sheer reach of that tail raised urgent questions. More observers joined in. A British imager and an Australian colleague independently captured 3 Atlas on different nights, using different filters and different optical trains. Their data repeated the same strange geometry. Behind the glowing core of 3 at last, the main tail fanned outward in the expected direction away from the Sun, along the push of solar radiation. Closer inspection revealed a second structure. A narrow, almost needle-like streak seemed to cling back toward the Sun, forming a reverse tail that appeared to cut straight into the oncoming flow of the solar wind while remaining anchored to Atlas. Comet scientists know that so-called anti-tails can appear under special viewing angles when dust sheets line up with the observer. Even so, the apparent thickness and persistence of the reverse feature behind 3i Atlas looked extreme compared to familiar catalogue members. Modelers started to do rough calculations in informal channels. To maintain such an extended reverse tail against a charged particle stream moving hundreds of kilometers per second, 3i Atlas would need to shed enormous amounts of material or rely on some other source of momentum. Mass loss on that scale would quickly strip a modest nucleus to nothing. Yet brightness estimates suggested that the core of 3i Atlas remained surprisingly robust for an object supposedly bleeding dust into a 5 million kilometer plume. On forums and preprint comment threads, a quiet split emerged. One camp insisted that geometry plus outgassing could still cover everything seen in the amateur frames of Atlas. The other camp pointed to the consistency of those civilian images captured on different continents under different skies, and argued that 3i Atlas might be advertising a behaviour that standard comet physics only barely describes. In those communities, trust flowed toward the raw stacked files because every pixel of Atlas could be downloaded, reprocessed and checked. For many viewers, awe mingled with unease as the scale sank in. A stranger from between the stars, 3 Atlas now dragged a visible structure across space that dwarfed every world in the inner solar system except the Sun itself. The official channels still spoke of a curious comet, but the amateur gallery told a louder story. The next question waiting in that story was about precision knot size, because the jets of 3 Atlas were about to reveal an even sharper paradox than a 5 million kilometer tail. By late summer, astronomers were no longer staring only at the vast tail of 3i Atlas. They were staring at the narrow jets of gas and dust that seemed to lance out of Atlas in a perfectly straight line. During July and August, several teams tracked periodic changes in the light curve of 3 Atlas. Those tiny regular flickers suggested that Atlas rotated roughly once every 16 hours, a comfortable spin for an oddly shaped interstellar body. On paper, a 16-hour rotation meant that any material venting from the surface of 3 Atlas should sweep across space like a paintbrush on a spinning wheel. If a camera integrated that motion over minutes, the resulting jet from Atlas should look twisted, broadened, or gently curved. That expectation is what made the November images so unsettling. In the best amateur stacks, the main jet from 3 Atlas did not look blurred or smeared. Instead, the dominant jet appeared as a sharp needle-like feature, extending in a single direction from 3 Atlas, as if someone had drawn a ruler straight through the coma. The feature remained aligned from frame to frame in a way that did not match what a 16-hour spin should paint into the sky around Atlas. Professor Avi Loeb took that misalignment and gave it a name, adding one more puzzle piece to the dossier on 3i Atlas. He called the paradox Anomaly 12, a shorthand for the clash between the measured rotation period of Atlas and the unnaturally straight stable jet geometry. In simple terms, if 3 Atlas really turns once every 16 hours, then the gas and dust should trace a spiral, or at least a fan, not a surgical beam. To keep a jet from Atlas looking that straight, either the rotation would need to be dramatically slower than measured, or some mechanism would have to constantly steer the outflow back into the same line. The first option forces another conflict with comet physics. Asymmetric outgassing tends to spin small bodies up over time, yet the observations around 3i Atlas hint at the opposite, a possible slowdown that standard models struggle to reproduce. The second option pushes the imagination further. A mechanism that keeps a jet from 3i Atlas aligned would need to respond to torque rotation and the changing sun object geometry, almost as if the vent were under active control. Most researchers stay cautious and look for more mundane configurations of vents and cavities on the surface of 3i Atlas. Even so, in private conversations, the phrase collimated jet comes up more often than many would like to admit when they study the profiles of Atlas. For people following the story from afar, the details of kinematics and integration times may sound abstract. Yet beneath the jargon, the core question is simple and visceral. How does something spinning in the dark keep drawing such a straight line through light? And what does that say about the engine inside 3 Atlas? As new data arrive, that question will not fade. The next layer of analysis turns directly to the energy budget of 3 Atlas, and to whether sunlight alone can really account for the power behind those disciplined jets. The question hanging over the latest data is no longer just how 3I Atlas moves, but how 3I Atlas powers that motion. Sunlight is officially the only energy source in the story, yet the behaviour of Atlas keeps inviting a different, more uncomfortable possibility. In the conservative picture pockets of surface ice on 3 Atlas hide inside cavities shielded until the sun hits them at just the right angle. When those wall regions warm up, the trapped volatiles in Atlas can vent in sudden pulses, producing sharp jets that look strangely straight in single exposures. NASA spokespeople have pointed to this scenario when pressed about the disciplined jets of 3I Atlas, framing the behaviour as an extreme but still natural configuration of cracks and pits. That patchwork can explain some of the timing, but the energy budget of 3I Atlas is harder to tame. At the distances involved, the sunlight-bathing Atlas is weakened again by the dark dusty surface that absorbs and re-radiates heat. For most comets, the thermal glow matches what the solar flux can reasonably deliver, and the gas production rates stay inside familiar envelopes. Observers now wait for infrared instruments, especially the James Webb Space Telescope, to pin down how much heat 3I Atlas truly radiates. If James Webb sees a thermal signature from 3 Atlas comfortably in line with solar heating, the conservative picture survives another round. If the glow from Atlas significantly exceeds what passive warming can supply, then the numbers begin to whisper about an additional source of power buried inside the interstellar visitor. In that scenario, 3 Atlas would no longer be just a lump of ice and dust responding passively to the sun, but something with an internal energy reservoir we do not yet understand. The tail geometry feeds the same suspicion from another angle. Using standard comet models, Professor Avi Loeb has estimated how much material 3I Atlas must eject to carve a 5 million kilometer main tail and a reverse structure that appears to push back into the solar wind. To let that anti-tail from Atlas stand up to a plasma stream moving around 400 kilometers per second, the expelled material needs enormous kinetic energy. Run the mass loss forward in time and 3I Atlas should erode, rapidly shrinking in a way that would dim the object far more than current brightness estimates suggest. This mismatch is what Loeb calls a mass loss paradox for 3I Atlas. Either the nucleus of Atlas is vastly larger than current constraints allow, or something about the thrust per unit mass is different from regular outgassing. In engineering terms, an efficient engine does not need to throw away as much reaction mass if the exhaust velocity is high. Ion drives and plasma propulsion on our own spacecraft already exploit that trick, though on a scale far smaller than what 3I Atlas appears to demonstrate. Seen through that lens, 3I Atlas could be behaving more like a deep space thruster than a passive snowball. A high-velocity exhaust from Atlas, perhaps microscopic particles or exotic ions, could in principle generate substantial acceleration while consuming far less bulk material than a classical comet. No one has direct proof that such a mechanism operates on 3 Atlas, and most scientists are careful to keep that idea in the realm of speculation. Yet the comparison between the apparent performance of Atlas and the best propulsion systems humanity has built is becoming harder to ignore. For people following from outside the field, the equations collapse into a simpler emotional response. 3 Atlas looks too bright and too intact for something that should be bleeding itself away to sustain a 5 million kilometer structure, and that dissonance feels like a secret engine humming behind frosted glass. If sunlight alone cannot fully explain the power behind Atlas, then the story of this visitor starts to blur the line between natural extreme and something more deliberate. As the community waits for thermal spectra radio scans and fresh imaging, the stakes rise with every new measurement of 3I Atlas. The next phase in the narrative will track how Atlas moves past Earth and bends through the gravity of Jupiter testing, whether this energy puzzle deepens into a pattern or fades back into ordinary comet physics. The first major test in this story arrives not at Jupiter, but much closer to home. On the 19th of December 2025, 3 Atlas makes its nearest approach to Earth, and every telescope schedule on the planet quietly bends around that date. On paper, the flyby of 3 Atlas looks uneventful. Atlas will still be roughly 1.8 astronomical units away, about 270 million kilometers from Earth, well outside any impact corridor. For most objects that far out, the event would merit a few technical memos, a handful of spectra, and then a graceful fade into the archives, Instead, the calendar slot for 3 Atlas is being treated like a stress test for the entire observation system. Ground-based observatories have carved out continuous blocks to follow Atlas from mid-latitude amateur sites up to national facilities in Chile, Hawaii and the Canary Islands. Space telescopes from Hubble to James Webb have penciled in windows to catch 3I Atlas at multiple wavelengths, mapping dust gas and thermal glow as Atlas crosses the dark fields between constellations. The goal everyone states officially is simple. The closest approach of 3 Atlas is the best chance to refine its trajectory, measure its rotation, and constrain how much material Atlas is shedding into space. Yet underlying that checklist is a deeper hunger, the need to see whether the jets, the tail geometry, and the energy budget of 3 Atlas really obey the rules written for ordinary comets. That is where the question of transparency becomes as important as the numbers. In earlier phases of the story, key images and datasets connected to 3 Atlas have arrived slowly, sometimes wrapped in vague explanations and limited commentary. Each delay has trained the public to wonder what 3 Atlas is really showing behind the scenes before the polished plots reach a press release. Professor Avi Loeb and other outspoken researchers argue that this milestone must be different. If 3 Atlas is truly just an exotic natural object, then agencies should feel no fear in releasing raw images, prompt spectra, and honest uncertainty ranges as Atlas sweeps through its closest point. If 3 Atlas carries anomalies that challenge existing models, those same agencies face a choice between softening the story or trusting the public with a more complicated picture of Atlas. For people watching from their own screens and backyards, the approach of 3 Atlas is not just a geometric event. It is a moment when the gap between what the instruments see and what the institutions say can finally shrink or widen. Wonder, skepticism, and anticipation all converge on a single date, because what happens around this pass of 3 Atlas will shape how the world reacts to everything that follows. Once the Earth flyby ends the path of 3, Atlas bends outward toward the giant of the solar system. The next waypoint for Atlas is a rendezvous with the gravity well of Jupiter, where any hidden agenda in the trajectory of 3 Atlas may become far harder to ignore. If the Earth flyby is a rehearsal, the real appointment for 3 Atlas sits deeper in the solar system. On the 16th of March, 2026, the path of 3 Atlas brushes the invisible frontier around Jupiter known as the Hill Radius. The Hill Radius marks the region where Jupiter's gravity overtakes the pull of the Sun for nearby wanderers. Inside that bubble, any small body can in principle be bent trapped or gently parked by the gas giant rather than flung straight back to interstellar space. Trajectory analyses show that the track of 3 Atlas threads close to this boundary, close enough that small changes in speed or timing could spell the difference between a clean escape and a lingering embrace. For a purely natural visitor, this geometry would count as an impressive coincidence, one more curious entry in the logbook of 3 Atlas. For anyone entertaining technological hypotheses, the same geometry looks uncomfortably like a rendezvous point, chosen on purpose by Atlas. Jupiter already hosts swarms of Trojan asteroids, ring arcs and radiation belts that challenge even hardened spacecraft. Any fragments released near the Hill Radius can be captured into long-lived orbits surfing the gravity of the giant while staying bound to the Sun. In that environment, 3 Atlas could at least in theory shed smaller structures, probes or seeds that remain behind long after the main body of Atlas resumes the outbound leg. Engineers sketch speculative timelines in which 3 Atlas arrives just heavy enough to perform the maneuver. At peri-Jupiter, small changes in velocity could allow Atlas to offload tiny payloads that drift into Trojan clouds, inner moons, or high inclination paths threading through the magnetosphere. Such seeds would then have a front row seat to the storm belts, radio bursts and particle streams that make Jupiter a natural laboratory, all while the parent object 3I Atlas silently accelerates away. Most dynamicists will stress that gravity alone can create odd patterns. A comet core can fragment in passing, and debris from 3I Atlas could simply follow the complex choreography of resonances and perturbations without any guiding hand. Yet in the SETI community, the March encounter is described as a strategic window, a period when any controlled behaviour by 3I Atlas would be most obvious. For observers on Earth, the scene feels strangely theatrical. 3 Atlas has already stirred questions about hidden engines and disciplined jets. Now the same object is on course to skim the very zone around Jupiter, where a patient surveyor would choose to plant instruments or caches of data. Whether the passage of 3 Atlas through the Hill sphere ends up perfectly mundane or quietly history-changing depends on tiny deviations in a few orbital elements. Those deviations, if they exist, will only show up in the most precise tracking of at last as the rendezvous date approaches. Beyond that point, the narrative of 3 at last either relaxes back into celestial mechanics or unfolds into something closer to mission design. Long before 3 at last brushes Jupiter's gravitational frontier, a pair of robotic witnesses are already waiting there. One of them is NASA's Juno spacecraft looping through lethal radiation bands while quietly preparing to listen for whatever at last might whisper across space. Juno carries a sensitive radio receiver designed to study the storms and auroras of Jupiter. For the encounter with 3 at last, engineers have programmed Juno to scan a broad range of low frequencies from tens of hertz up to tens of megahertz, hunting for any signal that stands out from the natural roar. In the official plans, Juno will treat 3 at last like any other source, a potential contributor to plasma waves or lightning-like bursts as Atlas passes through the outer environment of the giant planet. Behind the formal language, the same receiver gives scientists a rare chance to check whether Atlas emits any unusual radio patterns that do not match known cometary activity. Further out, the European Space Agency's JUICE spacecraft has already turned its cameras toward 3I at last. JUICE caught at last in November from a vantage point that no ground-based telescope can replicate, but the probe is so distant that raw data trickles home slowly through the deep space network. By the time the November observations of 3I at last finish downlinking and calibration, the calendar will likely read February 2026. That means some of the best early close-up measurements of at last will arrive only weeks before the passage by Jupiter, leaving little time to digest whatever surprises the data may hold. This lag creates a strange kind of informational parallax around 3 at last. Spacecraft near Jupiter listen in real time while their insights about Atlas travel back to Earth through narrow radio pipes always delayed by distance and bandwidth. On the ground, the situation around 3 at last is different but equally urgent. As Atlas dims and moves outward after the December flyby, only observers with medium or large telescopes under dark skies can still trace the fading tail and measure changes in the jets. Star parties form in rural fields as people aim their instruments at the coordinates of 3 at last, hoping to add a few more nights of data before the visitor sinks below practical reach. For many amateurs, there is a bittersweet awareness that each clear night with at last could be the last one they ever get because 3 at last will not loop back for a second season. In this final window, independent observers become an informal safety net. If 3 at last flares, unexpectedly fractures or shifts its behaviour in some subtle way, the first hint may come not from a major observatory, but from a stacked image posted by someone processing data in a spare bedroom. The combination of Juno's radio ears, JUICE's delayed snapshots and grassroots imaging forms a patchwork surveillance grid around 3I at last. That grid still has blind spots, especially when at last moves through regions close to the Sun from Earth's perspective, but coverage has never been so distributed for an interstellar wanderer. Emotionally, the arrangement feels precarious. 3I at last is about to cross one of the most powerful gravitational landscapes in the solar system, and humanity is listening through a handful of probes and a scattered archipelago of backyard domes. As the rendezvous with Jupiter draws closer, the question lurking behind every new data point is whether 3 at last will behave like a stressed natural body or like something following a scripted plan. The answer may depend on how we interpret the next shifts in brightness and trajectory, and on whether the propulsion of Atlas truly fits within the engines we already know. From the moment the first strange tail images appeared, some researchers quietly began framing 3 Atlas in engineering terms rather than purely astronomical ones. In that mindset, Atlas stops being just a wandering body and starts to look uncomfortably like a vehicle. If a hidden engine is pushing 3 Atlas, the numbers suggest it behaves more like a high-efficiency thruster than a boiling snowball. The apparent non-gravitational acceleration, the disciplined jets, and the mass loss paradox all hint that at last might be trading a relatively small amount of reaction mass for a surprisingly large dynamical effect. On spacecraft built by humans, ion and plasma drives already use this trick, accelerating tiny particles to enormous speeds to squeeze maximum thrust from minimal fuel. Scaled up to interstellar dimensions, a similar principle applied to 3I Atlas could in theory explain why the tail structures of Atlas stay powerful without stripping the core bare. That line of thought naturally leads to the shell hypothesis. In this scenario, the bright dusty envelope around 3 Atlas is not the main body at all, but a camouflage layer wrapped around a denser internal structure. As 3 Atlas approaches Jupiter, The outer shell could simply play the role of ablative shielding, burning and venting in ways that mimic a comet, while a more compact core rides safely inside. When at last enters the Hill sphere, that core might adjust its motion open hatches or release smaller units into stable orbits using the tail as both a smokescreen and an exhaust plume. To cautious dynamicists, this reads like science fiction stapled onto real ephemerides. To SETI theorists who have spent decades thinking about probes disguised as natural objects, 3 Atlas looks disturbingly close to the sketches they once filed under speculative. The geopolitical dimension follows almost automatically. If there is even a non-zero chance that 3 Atlas carries artificial material signals or data caches, the first nation to intercept or sample, Atlas, would gain an advantage that defies current strategic playbooks. Defense planners imagine what it would mean if a fragment from 3 Atlas revealed new physics-novel alloys or a functioning device. In those scenarios, Atlas becomes not just a research target, but a prize around which budgets, alliances, and clandestine missions might quietly pivot. Closed-door meetings, vague statements from officials, and subtle changes in surveillance priorities begin to look different when viewed through the lens of 3 Atlas. What once sounded like cautious messaging suddenly resembles narrative management, an effort to keep speculation about Atlas from outrunning the data. For the public, this mix of propulsion theories and political stakes wraps 3 Atlas in an aura of slow-burning tension. People sense that Atlas might be forcing institutions to choose between radical transparency and tight control in a domain where trust is already fragile. As 3 at last marches toward its encounter with Jupiter, the object now sits at the intersection of propulsion, physics camouflage speculation, and quiet rivalry between spacefaring powers. The next chapter in the story shifts from orbital mechanics to images and information, asking why some of the clearest views of Atlas have come from backyards while official releases remain strangely underwhelming. The most influential telescope in this story does not orbit above the Earth. It sits in a modest backyard pointed night after night, at the same faint smudge in Virgo the passing stranger called 3 Atlas. The telescope belongs to Paul Craggs, an amateur astronomer with professional-level discipline. While many people only saw a dim blur in online star charts, Craggs saw a challenge, and began to track 3 Atlas as soon as the coordinates became public. Using a solid but affordable optical tube, a sensitive camera and tracking software, he tuned himself. Craggs gathered hour-long runs of raw frames on 3 Atlas. Each clear night produced thousands of photons from Atlas buried in noise, until careful stacking and calibration pulled a structured form out of the background. The first composite shocked even seasoned observers. Instead of a vague haze, his image showed a bright spine, a luminous body with contours that suggested depth and symmetry along the length of 3 Atlas. Craggs did not sit on the result. He posted the stacked frame and crucially the processing step so that others could download the data and rework 3 Atlas with their own tools. Within days, analysts overlaid his profile of 3 Atlas against official thumbnails and found more fine detail in the backyard capture than in anything released from major missions. Faint halos, subtle gradients along the main axis and hints of side structures all appeared more clearly in the Craggs rendition of Atlas. The anomaly here was social as much as technical. For the first time in this saga, the sharpest publicly available view of 3 Atlas came not from a government observatory but from a private garden under a dark sky. People who had been following the anomalies in the tail and the jets took notice. Trust began to flow toward the feed where 3 Atlas could be inspected pixel by pixel rather than toward controlled releases that showed at last in softer focus. Craggs himself stayed cautious in his comments, insisting he was documenting, not theorizing about 3 Atlas. The rising attention around his work set the stage for a striking comparison, because the next big image of 3 Atlas to hit the public would come from NASA with a level of build-up that promised far more than it ultimately delivered. NASA chose a very different stage for its big moment with 3 Atlas. Instead of a backyard stack, the agency announced a highly promoted live broadcast centered on a new high-resolution image of Atlas taken by the Mars Reconnaissance Orbiter. Viewers tuned in expecting to see the most detailed portrait yet of 3 Atlas. The commentary spoke of advanced instruments and cutting-edge imaging as the host counted down to the reveal of Atlas. When the frame finally appeared, the reality felt strangely anticlimactic. The supposed flagship view of 3 Atlas showed only a small washed-out smudge, with almost no visible structure, a ghost where people had expected a spine. What puzzled many was the timing as much as the blur. The high-rise camera had captured 3 Atlas nearly a month earlier, yet the image of Atlas was only now being shown with little explanation, beyond references to processing backlogs and government shutdowns. During the stream, the technical discussion stayed shallow skating past questions about tail geometry jets or non-gravitational behaviour in the motion of 3I Atlas. As the broadcast ended, people who had seen the Crag's data could not shake the feeling that the official view of Atlas was oddly incomplete. The disappointment did more than dim a single event. It primed audiences to notice every gap between civilian frames of 3 Atlas and the curated glimpses offered from institutional channels, setting up a conflict over whose image of Atlas should define the narrative to come. The deeper analysts probed into the Crag's data, the stranger the outline of 3 Atlas became. Instead of a fuzzy rounded coma, Atlas presented a narrow elongated form that looked more like a luminous spindle crossing the starfield. Along the main axis of 3 Atlas brightness profiles showed a central core flanked by faint symmetric streaks. Those side structures seemed to rise from Atlas at matching angles on both sides, as if 3 Atlas were threaded by ribs or spars rather than random jets. Early radar constraints had already hinted that 3 Atlas was not a simple sphere, suggesting an object stretched far longer than wide. The Crag's contours reinforced that idea, painting Atlas as an almost cigar-shaped presence, with clear orientation in space. When modelers overlaid the trajectory of 3 Atlas on those shapes, a new discomfort appeared. The path of Atlas through the sky did not resemble the lazy drift expected from a tumbling rock, but carried a subtle sense of direction, a motion that seemed chosen rather than purely inherited from gravity. Skeptics warned against reading intent into the track of 3 Atlas, pointing out the perspective, and sparse data can trick the eye. Even so, for many viewers, the combination of symmetry and elongation made Atlas look less like debris and more like hardware. That perception mattered because narratives around 3 Atlas were no longer just about chemistry and dust. They were starting to touch on design, a word that changes the emotional temperature of any discussion about an interstellar visitor like Atlas. The emerging image of 3 Atlas now pressed directly against questions of trust and disclosure. The next step in the story would be shaped by how institutions responded to the growing gap between the structured silhouettes seen by civilians and the vague outlines offered in official briefings about Atlas. Side-by-side comparisons of 3 Atlas began to circulate within hours of the NASA broadcast. On one side of the screen, the backyard rendering showed layered detail and a structured spine for Atlas. On the other side, the official frame reduced 3 Atlas to a pale blur, a difference that ordinary viewers could recognize without any training. Forums, science channels, and social media threads filled with questions. People asked why a lone observer could tease such clarity out of 3I Atlas, while a flagship mission seemed to show less. They asked why a month had passed between the capture and the release of the NASA image of Atlas, and why the commentary had dodged the more difficult topics. The pattern was what unsettled many followers of 3I Atlas. First came delays in key datasets, then vague language around anomalies, and now a high-profile event that downplayed the most striking features seen in civilian images of Atlas. The gap between raw curiosity and polished narrative widened with each new mention of 3 Atlas from official channels. In response, a quiet movement grew around open data. Independent analysts urged agencies to publish full-resolution frames, calibration files, and time series for 3I Atlas, not just carefully cropped highlights. Amateurs stepped up, sharing not only their best images of Atlas, but also their worst, making every stage of the process transparent. Emotionally, the shift was subtle but profound. 3I Atlas had started as a distant curiosity, something people expected to understand through press releases and expert interviews. Now Atlas was becoming a reason to learn stacking software to read preprints, and to question who gets to define reality when a visitor arrives from between the stars. Trust did not vanish from institutions overnight, but it no longer flowed in only one direction around 3I Atlas. Many viewers began to treat official statements about Atlas as one data point, among many not the final word. That redistribution of confidence sets the stage for the broader context. To understand why 3 Atlas resonates so strongly, audiences reach back to earlier episodes when unknown craft were reported in near-Earth space, and over remote seas cases where photographs, radar, and testimony forced the same questions about secrecy technology and the limits of ordinary explanations. In the years leading up to the arrival of 3 Atlas, another kind of mystery had been quietly building in the background sky. As cameras became cheaper and tracking mounts more precise, the moon turned into a favourite target for the same kind of amateur observers now following at last. One recent clip recorded by a hobbyist, with a modest telescope and a planetary camera, shows a small luminous disk gliding across the lunar limb. Frame by frame, the object spins its edges, catching sunlight in a way that makes it look almost metallic. Then it banks and slides away with a smoothness that does not resemble tumbling debris. Analysts who study 3 Atlas notice familiar patterns in the discussion. Some commentators rush to label the disk as a satellite flare or a high-altitude aircraft, while others pointed out that the trajectory cut cleanly across the field in front of the moon at an apparent speed too fast and too steady for a drifting balloon. What stood out most was the quality of the data. Just as with 3 Atlas, every raw frame from the lunar sequence was posted for download, letting anyone measure the brightness, the rotation and the path themselves. For many viewers, the spinning disk near the moon became a kind of rehearsal. It trained people to ask whether a bright structured object moving with apparent intent could really be dismissed with a single mundane label, and it primed them to look at 3i Atlas through the same skeptical data-driven lens. Decades before, 3i Atlas lit up telescope forums, another remote outpost found itself at the centre of an unscheduled mystery. Off the coast of Brazil, Trindade Island hosted a mid-century naval program that looked on paper entirely routine compared to the saga of Atlas. The Brazilian Navy used the rocky island as a platform for weather and geophysical studies. Crews launched instrumented balloons, tracked winds and monitored sea conditions, with the same kind of disciplined repetition that now marks nightly observations of 3 Atlas. For weeks, logs from Trindade read like a checklist. Then the entries shifted. Sailors and officers began reporting strange lights and structured objects in the same skies where they expected only clouds and balloons, a tonal change as stark as the first anomaly reports around 3 Atlas. One evening, personnel on a nearby ship watched a glowing sphere skim the waterline and pace the vessel in silence before darting away at a speed that no known aircraft of the era could match. Another day, observers at the island station saw metallic shapes hovering near their research balloons as if shadowing the instruments, a pattern of attention that feels eerily familiar to people now following the path of 3 Atlas through our own sensor networks. These were not isolated sightings by lone witnesses. Multiple officers, technicians and civilian specialists signed their names to report stacking testimony the way modern amateurs stack frames of 3 Atlas. In retrospect, the Trindade program looks like an early case study in what happens when a strictly managed military experiment collides with phenomena that refuse to fit existing categories. That collision between routine and the unexplained is the same tension that surrounds 3i Atlas today, and it sets the stage for the moment when cameras on Trindade finally captured something solid enough to challenge even the most skeptical eye. When photographer Almiro Baruna raised his camera on Trindade, the routine mission snapped into legend. 4 frames showed a grey metallic disc veiled in a pale blue haze hanging over the sea, with a clarity that modern analysts now bring to 3 Atlas. Navy officers present on deck signed off on the sequence, and the Brazilian Ministry of the Navy later confirmed that the negatives were genuine, a level of endorsement that investigators of Atlas still dream about. Behind the scenes, a radar station logged an unidentified target in the same sector. Just a day earlier, a pairing of hard signal and hard image that still haunts anyone who wonders what truly moves above our world, while 3 Atlas passes overhead. Trindade left behind a template for our present dilemma, a moment when disciplined systems met phenomena that looked uncomfortably like technology. Today, that template hovers over every new frame of 3 Atlas, as analysts weigh whether disciplined jets and tailored trajectories can really be written off as chance. In both stories, institutions walk a narrow line between acknowledging anomalies and protecting their authority, while independent observers publish everything they see of 3i Atlas. The open question is whether we are witnessing rare natural extremes or engineered behaviour that hides in plain sight. As 3i Atlas recedes into deep space, that question does not leave with Atlas.